Hello. Good evening, sir. I will wait for two more minutes. Then I will start the class. As still your friends are joining. Yes, ma. I will start the class. Very good evening to all. My voice is clear, ma? Audible to all of you? Audible to everyone? Okay. So I will start the class. Fine. So in the previous class, we have discussed regarding the address sequencing, nothing but how to search the address for control memory. Okay. So as we have seen, we have 4 different methods for selecting the address for the control memory. See, the first one is the incrementer, which increments the address of the control address register to take the next instruction to be fetched. So that address will be given to your multiplexer. That is the first method. Second one is by using the conditional branching. See, as we have seen, we have 2 types of branching, conditional and unconditional branching. Unconditional branching means directly the control memory will take this branch address to directly to the multiplexer, then from there the control address register and given to your control memory. Okay, whereas for conditional, there will be some status bits which selects according to your branch logic which branch it should go or which branch address it should go. Okay, then it will test the condition whether it is true, then it will give this branch logic to the multiplexer. From there it will control address register, then control memory. If it is false, directly next step is to increment the control address register. So this is about your conditional branching and unconditional branching. So this is the second method from which we can find out the address for your control memory. Third step is using your mapping. Mapping is nothing but transforming the operand code into an address. So we'll be having some instruction code using the mapping logic hardware. It converts the instruction opcode into some address. So that address will be given to your multiplexer, which selects the address and given to your control address register from their control memory. And the fourth one is subroutine register. What is a subroutine register? When we are incrementing, there might be going to the some subroutine thing, nothing but where the subroutine is nothing but the instruction with which can be repeated any number of times in a main program. That is subroutine register. That is subroutine, right? So whenever you are incrementing and it will go to your subroutine, according to that one, the return addresses will be stored in a particular register called as subroutine register, and that address will again given to your multiplexer. So according to this one, these 4 techniques will be there for finding out the address in a for a control memory. So that is nothing but address sequencing. Understood? Right. So the next one is micro program example. So as we have micro programmed control unit has been established. So the computer configuration, the total computer configuration will be looking like in this fashion. Okay, so from this part to this one, this total will be your processor part, and this is the control unit part. So this is total is your CPU. Okay, so in this one, we'll be seeing that we're having 2 memories. One is the main memory, and second one is control memory. Main memory stores instruction and data, whereas control memory stores microprograms. Okay, now coming to the registers, the processor registers are 4. First one is the address register, AR. Second one is program counter. Third one is data register. Fourth one is accumulator. These four are processor registers. Okay, whereas the control unit has two registers, that is nothing but subroutine register and control address register. Okay, now see here, the information that receives the transfer of information among registers in processor is done using multiplexer rather than common bus, because the multiplexer will be having only single output by having multiple inputs, okay, depending upon the selection lines. That's why we are going for the multiplexer rather than common bus. Okay, so whatever the information you want in the register will be given using the mux. Okay, now coming to the data register. The data register can receive information from, first one is accumulator, second one is program counter or memory. The data register can receive information from accumulator, PC or memory. Okay, next one, address register can receive information from data register or from PC. Sarnoma, one is from coming from data register and one is coming from PC. So the address register can receive information from the data register as well as from the PC. Okay, any two of this one. Next one is program counter. The program counter can receive information only from address register. There is no other source. The program counter will receive information only from the address register. Now, arithmetic, logic and shift unit performs operations with the data from AC and accumulator and the data register. This can perform the instructions or the data coming from the data register and the accumulator. Okay, so this is about your the computer configuration. Up to here it is fine. Okay, now next we're going to the micro program example. So here, see here. Now as computer configuration is being set and the micro program control unit is also set, now the next one is to generate the code or to write the some micro program. Okay, so for this code generation is called micro programming. Okay, and is a process similar to conventional machine language programming, nothing but the programming the programming language which will be understood by the machine is called as machine language programming. So machine always understood only zeros and ones. So that's what, so whatever the micro program or whatever the assembly language we will be following will be converted into zeros and ones for better understandable of your machine. Okay, now computer instruction format. So this instruction will be having 0 to 15 bits. Okay, nothing but this is a 16-bit line, 16-bit instruction, right? So in this one, we will be having three different things. One is the address, the opcode, and the ith bit. The address will be of 0 to 10, nothing but 11 bits will be used by address, then 4 bits for your opcode, and the ith bit will be for the mode for an instruction or sign bit for a number or carry out of an adder, right? So this depends, this ith bit will be depending the whether it is a positive or negative, or whether it is a direct mode or indirect mode, whatever, depending upon the instruction what you have, depending upon the applications whatever you're going to use. So it are divided into three types. One is address, one is opcode, and one is ith bit. So for address, it will be using the 11 bits 0 to 10, then 11 to 14 opcode 4 bits, and the last bit 15th bit will be your ith code. So one bit for your signed bit or mode bit. Okay. So according to opcode, we have four bits used for opcode. So as we have used 4 bits for opcode, so maximum number of micro instructions we can use is 2 power 4, nothing but 16 micro instructions we can get. Okay. So for an example, we have used here for only 4 micro instructions which are generally used in your program. Okay. So still we have 12, they also being used, but they are not used so frequently. That's what I'm explaining only the only the micro instructions that are being used regularly. Okay. So first one is add, whose opcode is 4 zeros, as we have explained in the previous class itself. Okay. Add is a symbol whose opcode is 4 zeros. Then how it performs is given as your description. See here, what add will do. See, directly add R1 comma R2. If you write, it directly not functions as directly adding these two. There will be some micro operations to be performed internally. If you perform that micro instructions, then only the add will be executing. Okay. So that's what micro instruction will be having some series of micro operations. So here first we'll go to the effective address in your memory of the registers of the content of the registers. Okay, nothing but the content of memory in that memory will be having one effective address. In that address we will be having some data that will be added with the accumulator. This is nothing but the data which will be present from your destination operand. As I have told you in the example that add R1 comma R2. R1 is always destination operand. R2 is nothing but source operand. Okay. So destination operand, defaultly whatever the data is stored initially will be stored in your accumulator, whereas address will be stored in your program counter. Okay. Right. So the effective address in the memory, in that one will be having some data that will be added to the content of accumulator. Again, it will be stored into the accumulator. So this is the description of add operation, add symbol. Right. Next one, branch. The branch opcode is 0001. So here branch is nothing but in which branch we need to go, in which location it should go, or in which line it should go. So for that one we should have some condition. So if accumulator is less than 0, nothing but if accumulator is less than 0, nothing but means if accumulator is negative, then the effective address will be stored into program counter. If accumulator is negative, then then effective address will be stored into the program counter. If accumulator is not negative, is positive, then what it will do? It will directly increment the next instruction, nothing but increment the control address register. If AC is accumulator is negative, the effective address will be stored into the program counter. If AC is positive, then the then it will increment the control address register for taking the next instruction to be executed. Okay, so here accumulator is negative, so its sign bit will be always 1. If accumulator is negative, so you should see the ith bit will be 1. If it is 0, it is positive. Next one, store. Store is nothing but the opcode is 0010. So you want to store the accumulated data into the memory whose effective address is there. Okay, accumulator will be stored, the data present in the accumulator will be stored in the memory where it will be having some effective address, right? That is nothing but your store symbol. Next one, fourth one is exchange. 0011 is the opcode for exchange. So exchanging is nothing but exchanging the information from memory to accumulator and accumulator to memory. Is this fine, ma? Understood, ma? Getting my point? Please respond in chat box. Clear? Shall I move forward? Shall I move forward, ma? I'm waiting for your response. Okay. So this is about your computer instruction format. Will be having 16 bits of instruction format. In that one, the address is 11 bits, opcode is 4 bits, and ith bit is 1. So as opcode is 4, we'll be having 16 instructions. But for an example, I am showing only 4 as these are more used. Now coming to the micro instruction format. So what is the format of your micro instruction? So the micro instruction will be of 20 bits. Computer instruction will be of 16 bits. Micro instruction will be of 20 bits, whereas computer instruction will be of 16 bits. So micro instruction are divided into 4 types. This format will be divided into 4 types. Nothing but F1, F2, F3. These 3 are the fields of micro operation. Okay. Next one is CD. Nothing but condition. BR. Nothing but branch. AD. Nothing but address. Okay. So in these 4 types, the micro instruction format has been divided. So here F1, F2, F3, each field will be having of 3 bits each. So if we have in one field 3 bits, okay, so we'll be having how many number of instructions? We can have how many number of instructions? If bits are 3. Yes, 8. Nothing but 0 to 7. So 0, 0, 0, 2, 111 will be getting your 0 to 7 micro instructions. So like that, in each field will be having 3 bits. So F1, F2, F3 total contains of 21 instructions. See here, first one is always, actually it should be 24. But why I am saying 21 means the first one for 3 of the fields will be performing no operation. So nothing but when the opcode is 000, it will be symbol as no operation. For 3 of the fields, first one is no operation. That's why I'm telling from each one it will be having 7 instructions. So totally it will be 21 instructions. Okay. Now coming to the command, sorry, condition. Condition have 2 bits. So how many symbols or how many micro instructions? How many micro instructions? If the bits are 2 2 power 2 4. So 4 conditions will be getting. Similarly 2 bits per branch. So 4 branches will be obtained as 2 power 2 is 4. Address we have 7. Okay, so 2 power 7. 2 power 7 is 128, right? So 128 will be your addresses that it can accommodate, right? So this is about your micro instruction format. Now we will go the F1, F2, F3, CD, BR, AD. Okay, in detailed one. So these tables are very important, ma. You need to memorize this one because this according to this table only the problems will be coming. Okay, they will directly give the micro operation, find out the address. In that form they can ask. So please check that these 5 boxes whatever are there that are very important. Okay, first for F1, as I have told you, it has 3 bits, so 0 to 7. So first one is none, no operation. Similarly in F2 also no operation, in F3 also no operation. So the first one is there is no operation, that's what, so we can neglect that one. So remaining 1 to 7, 1 to 7, 1 to 7. So this total are 21 number of instructions, right? Okay, so first one is when F1 is 001, what micro operation it will do? It will add. The add symbol, nothing but the content of data register will be added with content of accumulator and then stored in the accumulator. Okay, this is the micro instruction format, ma. Okay, don't compare with the add in your computer instruction, right? So see here. So F1 is 001. When 001, it will the symbol is add, so the data register content plus accumulator content will be stored. Adding the result will be stored in your accumulator. Second one 010, the symbol is CLR AC, clear accumulator. Nothing but accumulator should be put 0. Next 011, increment accumulator. The accumulator will be incremented by 1 and the result will be stored in your accumulator. 100, data register DR to accumulator, DRTAC, data register to accumulator. So the content of data register will be moved to accumulator. This is the micro operation. What is there when F1 is 100? 101, data register to address register. Okay, so the content of data register will be moved to address register. So what is this 0 to 10? What is this 0 to 10? See in your computer instruction format, the address is of, yes, the address is of 11 bits. So in the data register, whatever the address of the content data is there, that is of 11 bits, will be stored into the address register. Understood this one? Next one, 110. 110, nothing but the program counter to address register. So the content of program counter, the address, starting address, will be stored into the address register. 111, the data register. 111 is nothing but write operation. Okay, so the whatever the data will be written into the memory of address register. The write operation will be performed. The writing, nothing but writing data into memory. will be performed when your F1 is 111. Okay, now coming to the F2, second micro operation field. So 00 no operation, 001 subtraction it will perform. The content of accumulator will be subtracted with the content of data register, and the result will be moved to the accumulator. Next, 010. This is the symbol for your OR. OR is nothing but adding or multiplying. Add. Okay, right. So OR is nothing but add. Okay, so the accumulator and data register contents, it will be checked bit by bit ma. Okay, so whatever the OR operation will be there, that will be stored into your accumulator. Similarly, 011 and operation, and is nothing but multiplication. So the content of data register or the accumulator will be multiplied bit by bit. Okay, stored into your accumulator. Next, 100, the read operation. Whatever the data is there in your memory will be read and moved to the data register. So 100 of your F2 will perform the read operation from memory. 101 accumulator to data register. The content of accumulator moved to data register. 110 increment data register. The data register will be incremented by 1, again storing in the data register. 111 program counter to data register. The program counter address will be stored into the 0 to 10 bits of, as PC mentioned means address, so 0 to 10 bits of data register. Up to here it is fine. Now we are going to the F3. So same, first one is no operation, second one is 001, nothing but it is XOR. So the contents of accumulator and data register will be XORed, given to accumulator. Next, 010 complement. The content of accumulator will be complemented, stored into the accumulator. 011 shift left. The content of accumulator will be shift left, then stored again into the accumulator. 100 shift right. 101 increment program counter. Program counter will be incremented by 1, stored again into the program counter. Next, 110 at address register to program counter. The content of address register will be moved to the program counter. Final one, 111 is reserved. It will be reserved for some instruction that will be used for some additional requirement according to our application. Okay. Regarding this, any doubts? So now we will take one example considering these three F1, F2, F3. So we'll be having, by assuming these three only, the 9-bit address for your micro instruction. Yes or no? Because each one is 3 bits. So there will be a 9-bit address, right? So for every micro instruction, there must be only 3 micro operations, 3 micro operation fields. as we have only F1, F2, F3, three micro operation fields. So that's why the micro instruction will be containing maximum of three micro operations. Okay, there might be chances of four micro operations, but it can't take because we have only three micro operation fields. There might be chances of less than three. So if we have less than three micro operation for any micro instruction, okay, so we will write the fields according to the micro operation we have, and the third one we will be taken as no operation. Okay, so suppose for an example, we will take this one. See, we have only two lines here. Nothing but the memory address, the content of address register in memory is stored into your data register, and the program counter is incremented by one given. So for F2, the first one is F2 100, and the second one is F3 101. Okay, so third one we don't have. So we are taking as no operation, as we have already F2 and F3 11, so we should have F1. So that I am taking as the micro operation, none operation, nothing but 000. So MSB 9 bits of micro instruction is F1, F2, F3. So this will be your 9 bits of your micro instruction. Understood this one? Understood this one? Okay, so depending upon the micro operations we have, maximum we can have three micro operations. Okay, if you have less, add one with your no operation. If you have only one, the remaining two will be your no operation. Okay. Now next, now we have finished the micro operation fields. Now we will go for the condition. As condition are of 2 bits, so we'll be having four conditions or four conditions, four micro operations, right? So see here, the condition 0, nothing but always equal to 1, nothing but unconditional branch. We have seen that unconditional branch, the status bit will be always stored with 1. So using this two status bits, nothing but 0, it will be unconditional branch, always equal to 1. Now coming to the 01, it is indirect address bit. So the condition is the data register, nothing but 15th one, yes or no ma? Condition. I told to you that the 15th bit of your instruction format will be your ith bit that determines the condition. Okay. Indirect address mode at data register 15. 10 sign bit of accumulator 15 accumulator. So whatever the accumulator data is there, okay, if the 15th bit is 1 or 0, that will be your sign bit. 11th one is in accumulator we are putting the value of 0. So these are the four symbols in your condition: unconditional, indirect address, sign bit, 0 value. Now coming to the next one, branch. Branch symbol will be also having four symbols. Branch instruction will be having always four symbols, as we have only 2 bits. So 0, it goes to the symbol jump. So what jump does? Jump. The condition will be tested. If condition is equal to 1, the address will be given to control address register. If condition is met, nothing but equal to 1, the address directly go to the control address register. If condition is not met, nothing but 0, the control address register will be incremented by 1 to get the next instruction. That the jump symbol will function. If tested condition equal to 1, the address will be stored into the control address register. If condition is equal to 0, control address register will be incremented by 1. Next, 0 1, nothing but call. So here call means we are going for the subroutine. Okay, we are calculating the effective address for each and every instruction. So we are calling, our program will be going directly to there. Okay, so what the function of call will be? First, the address will be stored into the control address register. Okay, then the control address register will be incremented by 1 using a incrementer. If condition is equal to 1, that will be stored into the subroutine register. If condition is 0, same as the jump, the control address register will be incremented by 1. Call means nothing. We are calling one address. So that address will be stored first in the control address register. Again incremented using incrementer. Control address register will be incremented. It will goes to subroutine register. If condition is met. If condition is not met, is equal to 0, then increment the control address register directly without going to the subroutine register. Next, 1 0. This is return. So you went to subroutine. Now you need to return from subroutine. So the subroutine register will be stored and given to control address register. Okay, return to the actual address. Return to the address register where my instructions are there, which are to be fetched next. 1 1 is nothing but mapping. What the mapping does? Transforming the opcode into address, right? So similar fashion, what we are doing is, in our computer instruction format, we have address 0 to 7, then opcode, then ith bit. Okay, so what we are doing there, for mapping purpose, we are writing our opcode directly to same as your opcode, right? So the data register will be having 11 to 14. In that one, the control address register will be having 2 to 5. So whatever the opcode present in your 11 to 14 will be stored into control address register from location 2 to 5, 2, 3, 4, 5. Okay, then what we are doing? We are making the remaining. See, if your 7-bit address is there, so already 4 bits done. The remaining 3 bits should be 0. First one is the sixth one. Sixth one is ith bit, right? That is 0 first. Again 0 and 1. Remaining 2 also 0. So 0, 1, 6 is 0. Then the opcode will be given into the control address register location. So that is nothing but your mapping process. Understood, ma? Up to here it is fine. Up to here it is fine. Right. So I will stop here because I don't want to tell all the things in one class. That's what I'm stopping here. Okay. If you have any doubts, you can ask me right now in the chat box. Any doubts? Any doubts? Yes, ma'am. As our first unit is, yes, sir, can you explain the flow chart? Which one, ma'am? Which flow chart? Which flowchart? That the computer configuration one. Okay. So the computer configuration one. Right. This one. Yes. So here the computer configuration looks like in this fashion. So see here, from here to this part, the right side part, this total part is your processor. See, CPU, as CPU consists of the arithmetic logic unit, memory, and registers. So no? Okay. So this is your processor part, which will be included with your control unit as we are doing our micro programmed control unit. Right. So here the information will be passed through each and every registers with the help of only mux rather than a common bus. Okay, so here we'll be having two memories. One is main memory where we can store our instruction and data. Second one is control memory where we can store the micro programs. Okay, now here we will be having four registers of the processor. Address register, the address register address will be size will be 0 to 10 bits. Program counter 0 to 10 bits. Next, data register 0 to 15, accumulator 0 to 15. And two registers in your control unit. The control address register, subroutine register. The address, whatever being stored into your given from your processor data, will be stored into your control address register, where size is 0 to 6. Subroutine, if we have, it will be stored into a subroutine register. Okay, the size of main memory will be 2048 into 16 bit instructions, but whereas control memory is 128 into 20. 20 bit address, 128 words. It can accommodate. Okay. Now, see here. The data register, from where we are getting the information for this data register, one is from memory, one is from memory, one is, sorry, one, the data register can receive information from, yes, sorry, from data register can receive information from your accumulator, one. Second one is PC or memory. PC or memory. Okay, as we have seen that the program counter is always address and accumulator will be having some data. The data register will be coming up at which data, then address will be given from your PC or memory. Next, address register can receive information using two. First is memory, okay, and the second one is data register. One is memory and the second is data register. Sorry, the address register can receive information from, sorry, this one, PC, and one is or the data register. PC or data register. The PC can receive information, program counter can receive information only from address register. The arithmetic and logic shift unit will perform micro operations with data from accumulator and data register. and places the result in the accumulator itself. Now coming to the memory receives its address from address register. Memory receives the address from address register. Input data returned to memory. Input data returned to memory come from data register, and data read from memory can go only to the data register. The writing data or reading data will be coming and will be going to the data register from the memory. Okay. If any subroutine comes, the register address will be stored into the subroutine, will be given to the mux. So from there, it can generate address register. Then address will be given to your memory. So from here, whatever the instruction is there, that will be executed. Understood? Understood? 4 register in main memory. Yes. Address register, program counter, data register, accumulator. Still, still, any more doubts? So for CSC people, as we have finished the first unit, so already your consult faculty, I guess, have asked the CRs to tell any doubts we have in the first unit. If you have any doubts, you let to know your consult faculty so that we can take a doubt session separately. If you have no doubts, then we will be giving the assignment questions that you need to submit, that you need to write down and scan and mail it to the concerned faculty. The same thing will also be there for IT people. So if you don't have any doubts, then we will start the quiz. So no doubts. No doubts. Then I will go for the starting the quiz. Yes, ma. Okay, then I am starting the quiz. Fine. So please write the quiz and don't copy. Okay. If anybody is writing on the same URL you want to cheat, then they will put absent without any hesitation. Okay. So I have started the quiz at 5:15. So 15 minutes will be given. At 5:30, I will stop. Okay. Thank you.